In this video, we're going to look at analyzing and making a sketch of exponential functions without using any kind of technology, and looking at some of the key features as we work our way through this. Exponential functions in the form of y equals a times b to the x power, they have a domain that is the set of all real numbers all the time. The reason is because if I have a base here, any number that's not 0, and no matter what I put as its exponent, I'm going to get a value. So therefore, none of the exponential functions in this form that we're working with will have a discontinuity. And if there are no discontinuities for these kinds of functions, that means the domain will be the set of all real numbers. Now the range, on the other hand, not necessarily. Now if I'm looking at the function here, I have 2 to the x plus 1 power. Now normally when I'm doing the analysis, I like to save the range for last to do after I get a sketch. But if I think a little bit about what I have, if I have 2 to the something power, what is the smallest number that can be outputted by taking 2 and raising it to some kind of power here? And the smallest output that you can get will be a number just a tiny bit bigger than 0. This part that I highlight is going to approach a value of 0, and then I'm going to take 4 away from it. And so basically it's going to be approaching a value of -4. And there's no limit on how large the 2 to the power of x plus 1 can be. So the range here should go from -4 to infinity. Now again, we're going to look at this on the graph and we'll confirm that statement for the range. X-intercepts. To find the x-intercepts of a exponential function, you're going to put in 0 for y. Now, not every exponential function will have an x-intercept because there's no guarantee that y equals 0 will be in my range. However, all exponential functions will have y-intercepts because of the fact that the domain is a set of all real numbers, and domain is x, and so if x is 0, I'm guaranteed to get an output. Now, the way I would solve this for my x-intercept, put in 0 for y, move the 4 over. Now, for the stage that we're at within our exponential functions, we're not going to use logarithms. We're trying to do all this without a calculator. So we're going to try to use the properties of like bases. So we need to take the 4, rewrite the 4 as 2 to a power, so that way we can continue to solve. Well, 4 is 2 squared. So 2 squared is equal to 2 to the x plus 1 power. Now, once we get in this stage, where I have the same base on both sides, I can work in the exponents and solve from there. So I'm going to say 2 equals x plus 1, so that way I can get the left and the right sides to equal one another. Subtract the 1, 1 is equal to x, my x-intercept is at 1, 0. Now the y-intercept would be next. So the y-intercept, we're going to put in 0 for x's and we're going to evaluate. So we'd have y equals, I need to zoom out so I can see my equation. We'd have 2 to the 0 plus 1 power minus 4, which is going to give me 2 to the 1 power minus 4, which is -2. So our y-intercept, in this case, is at 0, -2. Now, if I have 2 intercepts, now I require when we sketch curves to have at least 2 points. We have 2 intercepts, so we don't need to mess with finding another point. And let's figure out our asymptote, and then we're going to make a sketch to figure the rest out. All exponential functions in the form of y equals a times b to the x power are going to have a horizontal asymptote. We're going to have a horizontal asymptote of y equals, it would have been y equals 0, but I did a vertical shift in this problem where I moved it down 4 units. So instead of being y equals 0, it's now at y equals -4. Now let's work our way and start making a sketch. Now it's a real rough sketch just to get the basic features of what we have, and I'm going to go just with a 5 by 5. All right, so we know we have a horizontal asymptote at y equals -4, so I'm going to do a dashed line at about y equals -4. We have an x-intercept at -2, or excuse me, not an x-intercept. We have a y-intercept at -2. Now we're going to plot our x-intercept at 1, 0, and we're going to make our sketch of exponential function. So as I work my way to the left for this exponential function, it's going to approach the horizontal asymptote. And as I work my way to the right, it's going to continue to increase. So from the sketch standpoint, it's going to look something along those lines. Now we can finish our analysis, and we can identify if it's increasing or decreasing. Well, to identify that, you read the graph from left to right. So as I go work from the left side to the right side, the graph's going up. So this is going to be an increasing function. Now the concavity. Concavity, if I look at the curvature, the inside of the bend of the curve. So the inside of the bend is opening upward. So this is going to be concave up. Now the true way to tell if it's concave up or down is if as you work your way from the left to the right, if the slope is increasing. So the slope of the curve is getting steeper as I work my way to the right. That is concave up. Now, notice our range. We already did the range, but now that I have a sketch, I can look at the range. It gets very close to -4, and then there's no limit on how tall it can go. So we confirmed our initial suspicion about the range to be -4 to infinity. And lastly, we want to do the end behavior. So the end behavior of the function, we are going to describe it using limits. So the end behavior of our domain, so be the limit as x heads towards -infinity, this function of x is going to equal, you look at your graph, what happens as you go left? As I go left, the graph approaches the horizontal asymptote of -4, so that's what the limit's going to equal. And then I would do the right-hand side. So the limit as x approaches +infinity, and you go look at your graph, and say, well, what are my y values doing as I go way off to the right? They are going to continue to go up, and nothing's going to stop it. So we'll say the right side is equal to infinity. Now let's look at another one here. So I want to do the full-fledged analysis and find all the key features of this exponential function and try to make a sketch displaying all these features. And so we start working our way through the list. Now this exponential function, although it looks different than the one we did before, it's still in the form of y equals a times b to the x power. I just have some transformations that are happening by multiplying it by -2 and moving down 18 and doing some other things. But there still are no discontinuities in here because I can put any number I want to for x and make that exponent of 1/3 become a value. And I'm going to get a real number output. So no discontinuities, which means the domain is the set of all real numbers. Now for this problem, I'm going to save the range for after I get a sketch. So that way you can you'll visually be able to see where the range comes from. Now let's start working for our intercepts and see what we have. Now remember, there's no guarantee that I'm going to have an x-intercept for an exponential function because I need to have y to equal 0 somewhere within my domain. All my domain guarantees are that I'll have every possible x value. So I'm going to set y equal to 0. And we're going to try to solve for x if we can. So from here, I would add the 18 to the other side, and I would divide by -2. And when I do that, I'm going to end up with -9 is equal to 1/3 to the -1 minus x power. And I'm looking here at this problem, and before I proceed, I have to look and say, all right, I have +1/3 raised to the something power, and I need that to equal -9. And you ask yourself, is that even possible? Is it possible to take a positive number base and make it become negative just by changing its exponent? The answer is no. So therefore, since that is not possible, we don't have an x-intercept. All right, so this graph will never cross the x-axis. Okay, so well now let's go find a y-intercept because all exponential functions have to have a y-intercept because y-intercepts happen when x is equal to 0 and we have the domain of all real numbers. So I'm going to go put in 0 for my x. So I get -1 minus 0 minus 18. And we go to simplify. Well, 1/3 to the -1 power makes 3. And then I got minus 18. So -6 minus 18, -24. So my y-intercept's at 0, -24. All right, so when we go to sketch this, we're definitely not using a 5x5 graph. Now, my requirement is that we have 2 points to make our sketch, along with some of the other key features. We only have one intercept, so we got to go find a second point. Now, the way we would do that is we're going to start with our equation. All right, so just scroll back up so I can see. We got y equals negative 2 times 1/3 to the negative 1 minus x minus 18 power. Okay, so the only thing that we know is that we don't have an x-intercept, so y can't be 0. My approach here is it's much easier to guess or put numbers in for x and then evaluate their outputs than it is to pick a number for y and try to solve. Because we know we can put in any number we want to for x and get a real number output. So we need to pick a number for x. I would pick a number for x that is going to make this base here not be a fraction. Now we've already put in a 0 for x to get our y-intercept, and so let's put in some other number to figure this out. Now I'm going to pick the number that's going to make that negative 1 minus x equals 0. So I'm going to let x equal negative 1. Because if I let x equals negative 1, I'm going to have y equals negative 2 times 1/3. Negative 1 minus negative 1 is 0. And I got minus 18. 1/3 to the 0 is 1. That's going to give me y is equal to negative 20. So I have a point at negative 1, negative 20 for my coordinate. So the last thing that we need in order to make somewhat of a sketch is the asymptote. Now, exponential functions all have, in the form that we're working with, all have a horizontal asymptote. I'm going to write the kind. Horizontal asymptotes are written as y equals a number. The number of the horizontal asymptote is going to be the vertical shift. So negative 18, because exponential functions, just y equals a times b to the x power should approach 0. But I'm deducting 18 from that, so my horizontal asymptote is negative 18. Now we want to sketch. So because we have such crazy values to work with here, what we can do is we can we don't need to put a tick mark on our scale for every single one of these things. We have a point at negative 1, negative 20, and 0, 24. So if I wanted, I'll make my y-axis and my x-axis here. All right, and I'm just going to say, all right, we have negative 1, and we have to have a y value of negative 18. So I'm just going to label it. So I got negative 18, a negative 20, and a negative 24 being displayed. All right, and I need to put my horizontal asymptote. I got a horizontal asymptote at negative 18. We have a coordinate at 0, negative 24. And we have a coordinate at negative 1, negative 20. And then so we wanted to sketch what's happening. Well, if I'm looking at my points, as I work my way to the left to get from the y-intercept to that other point we found, it's got to continue going towards that horizontal asymptote on that side, which means as I go to the right, and I miss my dot, but as I go to the right, it has to continue to go down and work in this manner. So looking at that graph, we can identify that it is a decreasing function because as you go from the left to the right, you're going to be going down. Looking at the curvature, and in fact the change in the slope, as I work from my way to the left to the right, my slope is decreasing. It's becoming more negative. It's going to be concave down. Now another way to think of it is the curvature, the bend is opening downward, concave down. And we can do our end behavior. So that would be the limit as x approaches negative infinity. Basically, you go to your graph and keep trucking to the left-hand side and say, what are the y values doing as my x values continue to go to the left? They're going to head towards that horizontal asymptote of negative 18. So that's the left side end behavior. Let's do the right side end behavior. The limit as x approaches positive infinity for this function. So as we go to the right on this graph, we are going down, and there's nothing that's going to stop it, so we'll say it's going to head towards negative infinity. That's what we'll set our limit equal to. The only thing we haven't done at this point is we haven't done the range. So range is smallest y to tallest y. Well, there's no limit on how far down this graph's going to go. It's going to keep going down. So the left side of our range interval would be negative infinity. Now our right side of the range interval is how tall or how big of y values can you get? Well, I'm scrolling up and looking, it's bounded above by the horizontal asymptote of negative 18. So it's going to get very close to negative 18, but it's never going to get there. So we'll say it'll get to negative 18, non-inclusive on my interval.